As I said in the previous video, today's topic is tangent and normal vectors to a curve. Let's start with the definition of unit tangent vector. Let C be a curve with parametric equation r equal to r of alpha. So this r is a vector function of the scalar variable alpha, which represents the curve C. If the derivative of r with respect to alpha exists and is not equal to the zero vector for some value of alpha, then the unit tangent vector to that curve C at that alpha means at the point whose position vector is r of alpha, is defined to be this. It's denoted T alpha because it's going to depend on alpha, so this tangent vector will also be a vector function just like r. So that's why we write T alpha. This overhead arrow indicates that it's a vector. That is equal to, by definition, the derivative vector divided by its magnitude. Note that existence of the derivative ensures that this makes sense. Additionally, because we also require that the derivative not be the zero vector, so its magnitude is a non-zero scalar, so we can divide by that. However, there are two things that we need to understand very carefully and in detail. What do we mean by a curve? And how is this vector function actually related to a curve? That is one thing. And the second thing is, why are we calling this tangent vector to the curve C? Is it really going to be tangent to C? If so, why? So let's understand these things first. Let's first see the definition of curve, because we are only going to consider curves in three-dimensional space. That means this space. So we only see that definition. There is a more general definition. Let I be an interval in R, any interval, open interval, closed interval, half open interval, unbounded interval. I may be the entire R also. Any continuous function gamma whose domain is I and codomain is the three-dimensional space, that means R3, is called a curve in R3. It looks strange, no? Gamma is a function. How can a function be a curve? A function is a function, whereas a curve is a geometric shape. Let me explain. Consider the unit circle centered at the origin. Say you have your two-dimensional plane in which you have your rectangular system of axes, x-axis, y-axis, familiar things, which intersect at the origin, and you consider that circle which has radius 1 and which has its center at the origin. We call that the unit circle. From analytic geometry, you know that its equation is also this: x squared plus y squared equals 1. So this is the set of all points in the plane whose distances from the origin are all equal to 1. And those points, when considered together, form this circle. Okay, so it's a simple thing. Now this equation is something static. Nothing is happening here, in the sense that the equation at once gives you all these points. Suddenly you have the points and you have the circle. However, you also probably already know that this circle also has a parametric equation, which is this. Sometimes we use this for convenience in some situations. You can also consider x as this function of some variable theta, cos theta, and y as sin theta, where you also know what theta is. If you think of any point on the circle, then its coordinates are really cos theta and sin theta for some theta. And that theta is the angle made by this line with the positive x-axis, the smallest angle. Alright. And now if you vary theta in this interval, closed interval, from 0 to 2 pi, then correspondingly this point rotates along the circle. It starts its journey here, which corresponds to the value theta equal to 0. Because you can see, if you take theta equal to 0, cos 0 is 1, so x coordinate is 1 and sin 0 is 0, so y coordinate is 0. So that means corresponding to theta equal to 0, you are at this location, which is the intersection of this circle and the x-axis here, not that one. And then as you move your theta across this interval, theta increases, the point rotates. When, for example, theta becomes pi divided by 2, because theta is this angle, then the corresponding point should be this one. We already know its coordinates. The x coordinate is 0 and y coordinate is 1. Are we getting those values from these equations? If theta is pi over 2, then cos pi divided by 2 is 0, yes. And sin pi divided by 2 is 1. So like that, as theta moves in this domain, the point itself moves on the circle, and you can also think of the point as tracing, drawing the circle. By the time theta reaches 2 pi, the point comes back to this, because cos 2 pi is again 1 and sin 2 pi is again 0, 1, 0. So instead of looking at this figure as a static figure, which such a Cartesian equation at once instantly gives you, you can think of it as something which is being drawn in a process, and that process is dictated by these parametric equations as the independent variable, which we also know as parameter, moves in its domain. So there is a process, a motion, and we want this type of description for curves in mechanics, because ultimately we are going to describe motions. In that sense, we say that the continuous function gamma from I to R3 is called a curve. But still it's not clear how this is related to this. In this case, I already know that this is the Cartesian equation of my circle, and this is parametric equation. Okay. Then what is that R of alpha in this case, and what is gamma in this case? Let's see. In this example, that interval I is this closed interval 0, 2 pi, and our function gamma is, say it's a function of theta, because here theta is the independent variable, is this function. Gamma of theta is cos theta, sin theta, 0. Although we have the curve in this two-dimensional plane, but after all it's also in 3D space. So that's why I have included the z coordinate also. You can imagine the z-axis like this. Okay. So in this three-dimensional space, the gamma tells me how the curve is appearing, where it is, and how it is being drawn also. As I said just now, that as my theta changes from 0 to 2 pi, the curve gets traced in three-dimensional space and it becomes the circle. So the reason for calling gamma itself as the curve is that gamma has more information than merely the circle. It not only tells us that the curve should be this circle, but it also tells us how to draw the circle. If you want to really be strict about calling only the geometric object curve, then the curve is nothing but the image of this function gamma, gamma of I in three-dimensional space. Okay, but there are more things, right? Why do we need gamma to be continuous? I won't go into too much details about that, but I will just tell you that there is an area of mathematics called topology, where there is a result which tells us that if we have a function from one space into another space, which is continuous, and the first space is in one piece, that is, it's connected, then the image of the function, or well, not exactly the image of the function, but the image of the first space under the function will also be in one piece. It will also be connected like this. This is connected. There is no gap, right? It's a continuous interval from 0 to 2 pi. If you see this interval on the real line, it will be a line segment whose endpoints are 0 and 2 pi. So in that sense, it's connected. It's in one piece. Is this function continuous? Yes. It's a function whose output is a point like this. And from a result from calculus, we know that such a function is continuous if and only if these individual component functions are continuous. Cos theta is a continuous function. Sin theta is also a continuous function, and the constant function 0 of course is also continuous. So that is why this gamma has those properties, and this is connected, so that's why the image of this under gamma, which is our circle, is also in one piece. That's why we need continuity. Alright, but then what is r of theta? I mean, r of alpha means in this case alpha is theta, but where are vectors? We do not see any vectors there. Well, we do have vectors there. This is that vector function, r of theta, which is cos theta I hat plus sin theta j hat plus 0 k hat, if we want to consider that also, where I hat is the unit vector in the positive direction of x-axis, j hat is the unit vector in the positive direction of y-axis, and k hat is the unit vector in the positive direction of z-axis. So this is actually the position vector of this point relative to this origin as your origin. Okay, that we always have when we consider vectors. So it is that function. And we are talking about differentiating this function with respect to theta, whose meaning we already know, and that's how we define unit tangent vector. So next comes the question of why should that vector be tangent to the curve? So this is our curve C, given by this function gamma, which maps some interval I in the real line into R3, three-dimensional space. Gamma is continuous, now you know. And what does gamma do? Gamma takes some point alpha from this interval I as its input and gives us this point in 3 dimensions as the output. And as alpha changes in I, this point also changes, and that's how the curve gets traced. And there is one more thing which also comes with this type of parametric equation of a curve. As alpha increases in I, you think of the example we saw just now, where the interval was the closed interval 0, 2 pi. As theta increased from 0 to 2 pi, that circle got traced like this. There is a direction and orientation in which things go according to that function. Like this, not like this. So this is an oriented curve. It's not merely just a curve. Okay, so that fact is also there, and the orientation goes in that direction in which the independent variable alpha increases. Say our curve has this orientation, which means that as alpha increases in I, the point traces the curve like this, and corresponding to some fixed point as the origin, we also have position vectors of points on the curve. That general vector is r of alpha, that r of alpha, which is of course going to be this gamma 1 of alpha. I mean, it's just a simple thing, no? And this I hat, j hat and k hat are unit vectors emanating from this point in some manner. Okay, they are mutually perpendicular, they form an orthogonal basis. All those things are there. Now next we come to the derivative, which by definition is this. Limit h tends to 0 of r of alpha plus h minus r of alpha divided by h. I think in the original definition I used delta alpha here. You can use any name, it's a variable after. Alright, now we are going to see how we can link this and this to try to figure out why this should be tangent. I mean, why should it be related to tangents? What is r of alpha plus h? This position vector. What is r of alpha? This position vector. So we can find what this difference vector is. Note one more thing, what did I say just now? That the curve is oriented in this way, which means that this is the direction in which things go as alpha increases. Now this point should correspond to a larger value of alpha then, which means that here h is positive. Okay. So with this understanding, let's now draw the vector this minus this. First, only that vector. It is this vector, right? Because by the definition of vector addition, this plus this is this. So obviously this will be this minus this, right? Now this is not exactly, although it looks like a tangent to this point, but it's not, okay. It's just that the curve is like this and somehow things got adjusted that it looks like tangent. But you can imagine that it's just a chord of this curve. Now as your point moves towards the original point means this one, we are treating this one as fixed. For a fixed given alpha, we have got this point. As this point moves towards that means what? Considering smaller and smaller values of h. That's what it means. Or in other words, h approaching 0, while all the time being positive. Then the point goes like this. Correspondingly, this position vector changes. Correspondingly, this chord vector also changes. It changes like this, and in the limiting case, this chord coincides with tangent. Okay. But we are not exactly seeing this vector itself here, but the vector divided by a real number, h, which is positive. Because we are dividing a vector by a positive real number, this vector does not change its direction. It maintains this direction. It does not matter in what way it changes as this point slowly approaches this, but that general direction does not suddenly get flipped and becomes that direction. Okay. So it maintains this sense even as it changes. And in the limiting case, you get a vector in this general direction which coincides or which lies on the tangent to this curve at this point. Alright, but a confusion arises here. This is a two-sided limit. Whenever you see an ordinary limit like this, it's always a two-sided limit. H has to approach 0 from the right side as well as from the left side. We should also consider negative values of h. Things will drastically change if we consider negative values of h here. Let's do that and let's see what we get. Because our curve is oriented in this direction, if we take a negative value of h, that means our corresponding alpha plus h is less than alpha. So the corresponding point on the curve should lie on that side. That is because as your independent variable changes in I and it's increasing, alpha plus h is attained first and then only alpha comes. So this point comes first and then this point. And because things are moving in this direction, so that is why that point lies on that side. Okay, but the definition of derivative does not change. It does not care in which side this r of alpha plus h is. So now things have changed. That same difference now is this vector. It's kind of pointing in the opposite direction, opposite to what's happening in the curve, how the curve is being traced. But then if this time this point, h again approaches 0, but all the while being negative, that corresponds to this point slowly moving towards this point, that direction does not change. That direction stays in that direction. So then, but we are saved by this h. It is pointing in that direction, but when you divide by a negative real number, it gets flipped. So we get back that general direction even in this case. And in the limiting case, as this point approaches this, still this chord coincides, it approaches the tangent, but at the same time the vector is pointing in that direction. So you are not only getting a tangent to this curve at this point, a vector I am talking about, but you also see that the vector kind of points in that direction in which the curve is oriented. It's as if at that point, that is the sudden instantaneous direction in which things are going. Do you see that? So that is why there is no problem with this definition. Why unit tangent though? Well, that's because this vector may not be a unit vector. That is why we divided by magnitude to get a unit vector. What we are discussing are really some ideas from an area of mathematics known as differential geometry. Although that's a fascinating area in its own right, but that's not really our aim. Our aim is mechanics. But to be able to even talk about the things in mechanics in a mathematical way, we need so many things. That's just the way it is. You need a lot of mathematics to even start doing physics. But anyway, let's now see one example in which we have a concrete curve given by a parametric equation and we need to find unit tangent vector, and that is this cycloid with this parametric equation. Well, you can again say, where is that vector r of alpha? That vector itself is not given, but its components are given. This times I hat plus this times j hat plus 0 times k hat will be that r of alpha. Alpha in this case is theta. So the equations that you see here are these: x equals a times theta minus sin theta, y equals a times 1 minus cos theta, and z is equal to 0. This part indicates that actually the curve is lying on the xy plane. That won't always be the case, okay? But in this example it is, where a is some fixed positive real number and theta varies in this interval. So it is that I, right? And the curve looks like this. You can see some 1 or 2 points. What do we get when we cannot actually put theta equal to 0 or 2 pi, which just means that the end points are not there in the curve. But still, just to understand why the figure is like this, if you take theta equal to 0 here, what are you getting? 0 minus sin 0 is 0, so x is 0. cos 0 is 1, 1 minus 1 is 0, y is also 0. So that corresponds to this point. It matches. I mean, when theta is very close to 0, the point is very close to 0, 0. What do you get when you put theta equal to 2 pi? Here you get 2 pi, sin 2 pi is 0, 2a pi. Cos 2 pi is 1. So again you are getting 0. 2a pi comma 0, and z of course is 0. If instead you take theta equal to the middle point, say pi, then what do you get here? A pi minus sin pi, a times pi minus sin pi. Sin pi is again 0, so you get a pi. And this time, what is cos pi? Cos pi is minus 1. So minus of minus 1 is plus 1. So here you get 2a. A pi comma 2a. That's the highest point here in this figure. Find the unit tangent vector to this curve at the point corresponding to theta. That means at a general point. Solution: let I hat and j hat be the unit vectors in the directions ox and oy respectively. The usual stuff. The position vector of any point on the cycloid is then any point related to this O. Okay, I should have written that, but I forgot. Is then of course R equal to the x component, which is a times theta minus sin theta I hat, plus the y component a times 1 minus cos theta j hat. Since the k component is 0, k component means z component, okay, because that is 0, so we did not even bother to write k hat, because that anyway won't appear here. So to find the unit vector, unit tangent vector, what should we do? We have to first of all differentiate this with respect to theta. The derivative is pretty easy to find. Note carefully that those unit vectors I hat and j hat are constant with respect to what? With respect to theta. As theta changes, the point on the cycloid changes, it moves on the cycloid, but I hat and j hat do not change. So although you should really ideally use the laws for differentiating vector functions, that means when differentiating this part, you have to differentiate this keeping I intact, and then in the next term you have to keep this intact and differentiate I, but that next term vanishes because I is constant, it does not change with theta. So that is why we have to just, this is going to mostly be the case that these basis vectors won't change with respect to whatever parameter we have. So in most cases you just have to differentiate the component, treating these things as they are, that means they are constant. So when you differentiate this ordinary real valued function with respect to theta, what do you get? A is constant, a times 1 minus cos theta. Derivative of sin theta is cos theta. That times I hat plus a times 1 of course gives you 0. Cos theta has derivative minus sin theta. Already there is a minus, so a sin theta j hat. And next we find its magnitude. So the square of the magnitude of this vector we already know is the sum of the squares of the components a square times the square of 1 minus cos theta plus a square sin square theta, which if you take a square common out and expand that square, it becomes this 1 minus 2 cos theta plus cos square theta plus sin square theta. These two terms give you 1. 1 plus 1 is 2, and then you can take 2 outside, having 1 minus cos theta here, and then you use the trigonometric identity that 1 minus cos theta is 2 sin square theta divided by 2. That 2 and this 2, they become 4. So then you lift square and you get this 2a sin theta divided by 2. Already it was given that a is positive, okay. So when you lift square, it makes sense that you write a. Actually you should write mod a, but that is equal to a. Sin, however, is not always positive. but sine theta divided by 2 will be positive. You think why? Okay, I won't tell you, but we have now this. So now we have to divide this vector by its magnitude to get the unit tangent vector. So t of theta is this divided by that magnitude, which was 2s sine theta divided by 2 times I hat plus this divided by that same thing times j hat. Then after again applying similar trigonometric identities and doing some calculations, this is what you get as your unit tangent vector, sin theta over 2 I hat plus cos theta over 2 j hat. So let me just end the video here, and in the next video we will see unit normal vector. There is another unit vector which is always perpendicular to the tangent, also at that point where we have the tangent to the curve. That's called the normal vector. That's also related to the tangent vector, not simply just in the sense that it's perpendicular to the tangent vector, but there is something else also that we will see in the next video.